All right, today we're going to take care of the rest of section 10.4. We have two theorems left and a couple of numerical problems that'll go along with those. So we'll start off with the first of the two theorems. Here it is. It goes like the following. A right triangle can be inscribed in a circle if and only if the hypotenuse is a diameter. So feel free to pause the video and jot that down. A right triangle can be inscribed in a circle if and only if the hypotenuse is a diameter. So what we've got going in the picture, when you have a chance, is we have a diameter that goes from A to B. So of course that means it has to pass through the center. So AB is the diameter of the circle. And then if we form a triangle using that diameter and an inscribed angle, let's say it's here at D, then no matter where you place D, that triangle has to be a right triangle. So the important word there that we end up with is we have a right triangle at the end. We have a right triangle at the end of this, all right? The idea, again, hopefully you remember from the first part of 10.4, since the angle at D is an inscribed angle, so this angle right here at D is inscribed because it's formed by two chords and the endpoint is on the circle. And because AB is a diameter, that means the arc from A to B has to be 180 degrees because it's a semicircle, half circle, and therefore the angle is going to be half of the intercepted arc. So no matter where we place D, the triangle is going to be right. Okay, as long as AB is a diameter, that's always going to be true. So what's interesting is if I start you guys off with a diameter, the diameter going from A to B through C, just like we had a second ago, then no matter where I place D, so if I place D right here and connect D to A and D to B with two chords, this must be a right triangle. If I were to place D up here somewhere and connect D to A and D to B, then this has to be a right triangle. If I would have placed D over here somewhere, if I connect D to A and D to B, that forces the angle to be 90 degrees. If I have one color left here, if I were to put D really, really close to A, but connect it to connect D to A and then D to B, that angle is going to be a right angle. So no matter where you place D, as long as AB is a diameter, so again, the important part, this AB has to be a diameter, then wherever you place the angle, it's going to be 90 degrees, and therefore we have a right triangle. Therefore we have a right triangle. Okay? So a numerical problem that uses that idea would be something like the following. So feel free to pause the video if you want to jot the problem down before I start talking it through. So pause the video if you wish to get the picture. This is a good one for your notebook to have for your test. Right, so once you have the picture down though, I'm asking you for the four angles that you can see in the diagram, 1, 2, 3, and 4. Okay, and there's a whole bunch of different places to start, so this isn't the only way you can get there. But here's one. Since the angle located at A is inscribed, the angle at A is formed by this chord to B and this chord to C, right? That means that the angle, 28 degrees, and the arc, BC, this arc, our theorem from early in this section says that the angle is half of the arc, or backwards, the arc is 2 times the angle. So this arc, BC, is going to be 2 times 28, which is 56 degrees. Okay? I know that's not one of the questions, but then because angle 2, let me choose a highlighter tool here, because angle 2 is a central angle is always going to be equal to its arc. So angle 2 is going to be equal to the arc, so angle 2 would be 56 degrees. So there's something from early in the chapter. Then, the theorem that we just talked through, since the chord from A to C goes through the center, O, AC is a diameter. I'll just put a little arrow in there. So AC is a diameter. Therefore, if we complete the triangle, which is what we just talked through, at B, then all of angle B, not just one part, but all of angle B is 90 degrees. All of angle B is 90 degrees. Okay, so we keep that in mind. Big angle B is 90 degrees. Again, I know that's not one of the questions, but you can then see that angle B is made up of angle 1 and angle 4. So we know angle 1 plus angle 4 is equal to 90 degrees. So if we can find one of those, then we'll very quickly be able to find the other one as well. Okay, so how can we get to the other one? Well, since angle 2 is 56 degrees, okay, we're then going to be able to find angle 3 and angle 4 relatively easily because, let me change colors on you, because the triangle formed by OBC, that triangle has to be isosceles. It has to be isosceles because two of its sides, O to B and O to C, OB, OC, are radii. And all radii of the same circle have to be equal to each other. So therefore, angles 3 and 4 have to be equal to each other. So if angle 3 and angle 4 have to be equal to each other, and we know the three purple angles add up to 180, so 56 plus angle 3 plus angle 4 add up to 180 degrees. But since angle 3 and angle 4 are equal to each other, we can replace one with the other. That's called a substitution. So I can replace angle 4 with what it's equal to, and now I can solve. Angle 3 plus angle 3 is equal to 2 angle 3's. And if I move 56 to the other side by subtraction, what I'd be left with is 2 angle 3's is equal to 124. So I can divide by 2, and angle 3 then is going to be equal to 62. But since angle 3 and angle 4 are equal, if angle 3 is 62, angle 4 is 62. And then finally we go back to the fact that all of angle B, big angle B, is 90 degrees. And now that we found angle 4 is 62, now that we know angle 4 is 62, I can replace angle 4 with 62 and solve for angle 1 by subtracting 62 from both sides. And therefore, angle 1 is going to be equal to 90 degrees minus 62 degrees, which is 28 degrees. And we have all 4 of the missing angles. Okay, so that's the first theorem, and a decent numerical problem using some of the, at least part of that idea. Okay? Like always, feel free to pause the video if I'm going too fast for you. But the second theorem then, the second theorem is this one. This one finishes off section 4. Quadrilateral. So of course, quadrilateral means four-sided shape, so four-sided polygon. So a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Okay, so quadrilateral, four-sided shape, can be drawn inside of a circle, inscribed in a circle, if and only if opposite angles are supplementary. So we've been using this word almost the entire year. Supplementary means add up to 180 degrees. We know what opposite means. So what the theorem is saying is we can put a quadrilateral in a circle if and only if opposite angles, the way I've drawn this one, 2 and 4 add up to 180 degrees, and also 1 and 3 would add up to 180 degrees. Okay, so that's the second theorem. Quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Alrighty? And then, pardon me, I think I have two numerical problems that'll go along with that. So here's the first one. And like always, feel free to pause the video if you want to get the picture down in your notebook before I start talking it through. So feel free to pause right here. Right, and now we'll go ahead and solve it. So you can see in the picture that we have a quadrilateral. We have a 1, 2, 3, 4-sided shape, so quadrilateral. And what the theorem says is that opposite angles have to be supplementary. So opposite angles going this way have to add up to 180, so that allows us to say 104 plus 2y has to add up to 180 degrees. And also opposite angles this way, 5x and 110 have to add up to 180 degrees. Obviously giving you two relatively simple equations to solve. Move 104 to the other side by subtraction. And get rid of times 2 by dividing. So the value of y is going to be 38. And for the second equation, subtract 110 to the other side. And get rid of times 5 by division. So x is going to be equal to 14. Right? So you can find the value for the variable. So there's a relatively easy numerical example. And then I'll finish with one that's a little more difficult. Again, feel free to pause the video at any point to get the rest of it down so you have it to use in both homework and on your test. Okay, so here's the last one. And this one's going to be a little more difficult, a little bit tougher. All right, but let's see if we can run it through. Once again, we have a quadrilateral, 1, 2, 3, 4-sided shape inside of a circle. What the theorem says is that opposite angles are supplementary. So those opposite angles have to add up to 180 degrees. And these two angles have to add up to 180 degrees. Problem is, of course, what's making this one more difficult is we don't know the angle at F, and we don't know the angle at E. All right? So in general, we know that the 12x located at G plus angle E has to add up to 180 degrees. And also 3y, which is the measure of the angle at H, plus F, the angle directly opposite, has to add up to 180 degrees. Okay, we know those opposite angles have to add up to 180. That's what the theorem says. But our issue is we don't know what E is. We don't know what F is. So we have a little bit of extra work. Okay, and I'm going to choose some bright colors here to help out. I'm going to ask you to first focus at F. Angle F is formed by the chord from F to E, and then the chord from F to G. So one more time, angle F is formed by a chord that goes from F to E, and then a chord that goes from F to G. And what I need you to notice is that the arc that those two chords intercept go from E through H around to G. And since F is on the circle, F is inscribed, which means it's going to be half the arc. So angle F is going to be equal to half of the arc. The problem is the arc is made up of two chunks. It's made up of the chunk from E to H, which is 96 degrees, and the chunk from H to G, which is 45 degrees. So we have two operations to do. We have to add and then multiply by a half. So let's see, 96 and 145. I think that's going to be 141. I think I'm doing that okay in my head. Let me double check. Yep, I think that's right. And then when we take half of that, half of 141 is going to be 70.5. All right, so we found F. So therefore, we can now pick up what F is and put it into our equation where we were adding the opposite angles. So now I can replace F with 70.5, excuse me, and solve the equation. So we'll move plus 70.5 to the other side by subtraction. And I'm going to double check myself on my calculator to make sure I don't mess that up. So that's 109.5. And to get rid of times 3, divide. And what we get is 36.5. So y would be 36.5 degrees. Okay, and then we're just going to do something similar for E. So that we can take our first equation here, replace E with what it's equal to, and then solve the equation. Okay, so changing colors here so you can see it. Angle E on the circle, is made up of the chord that goes from E to F, and then the chord that goes from E to H. And therefore its arc is this one. The arc would be the one that starts at H, goes through G, all the way around to F. And we know that the angle is going to be half of the arc. But again, the arc is broken up into two chunks. One chunk, H to G, is 45. And then the other chunk from G all the way around to F, and that one's missing. That one's not there. That one is not there. But we know that when we add the four arcs together, the 48, the 96, the 45, and the one that's missing, they form a complete circle. So if we subtract all of those away from 360, whatever's left over, which is 171, has to be that missing arc. Okay? So then to find E, again, it's two operations. It's 45 plus 171, which is 216. And then half of 216 is 108. So wherever we see an E, right there, we can then replace it with what it's equal to, which is 108, and solve for X. So we move plus 108 to the other side by subtraction. What is that, 72, I think? And then get rid of times 12 by dividing. And so X is going to be equal to 6. Okay. So that's the last numerical. I'm just going to move my screen here. Yep, that's the last numerical problem I was going to do for you. So you're all done with section 4, so you can finish off the assignment. You have plenty of time during this class period. All right, so you can put your phones away, put all that crap away, get out the assignment, and go ahead and get started. All right, we'll talk to you tomorrow.